Hello all, welcome to this channel cfdbaba. This is the part 2 video of flow inside lid-driven cavity. In part 1 I have shown how to import the mesh from Salome into OpenFOAM. To view the procedure of how to import mesh into OpenFOAM, you can watch the part 1 video first if you haven't watched it yet. Now we need to set the correct boundary condition names in OpenFOAM case folder. Here we can set the boundary conditions in 0 folder. Go in 0 folder and here you can find the velocity and pressure file for setting the initial boundary conditions. Let's first open the U file. You can open the files with Notepad++. I use this text editor for editing the files in OpenFOAM case structure. You can see the names already from the tutorial of lid-driven cavity that we had copied from OpenFOAM folder. This is the reason why I set capital W while naming the moving wall and the fixed walls, because this name is already available in the tutorial case. The only thing we need to change is front and back. Instead of front and back, the name of our boundary is default faces. You can also view the name of your boundaries by going inside the constant folder. Go inside polymesh folder and here open the boundary file. You can see the names of the boundaries that have been assigned to our mesh. We have the moving wall, we have the fixed walls, and we have default faces, which is the front and the back face. Copy this name and paste it instead of front and back. The default faces will be assigned the empty boundary condition so that OpenFOAM software understands that we do not want to simulate anything in the Z direction. So it will only solve for values in X and Y direction for velocity as well as pressure. We are applying a fixed value of 1 meters per second to the moving wall, which is the top wall of our geometry. Internal field defines the initial boundary condition in the entire domain for the velocity. Here we have specified that the velocity is 0 in X, Y and Z direction. For a moving wall, we have specified that the velocity is 1 meters per second in the positive X direction. That is, the wall will move from left to the right side. We have assigned no slip wall boundary conditions for the fixed walls, and we have assigned empty boundary condition for the front and back face, and it has been named default faces while getting imported into OpenFOAM. You can see that Salome has automatically named those two faces as default faces. Now we need to change the pressure boundary condition. Go in the 0 folder and open the pressure file. Here we just need to change the name of the boundary. We will copy the name of default faces and paste it instead of front and back. Save this file. We are applying 0 gradient boundary condition on the walls and empty boundary condition on the faces for pressure. 0 gradient means that the pressure will automatically be calculated on these two boundaries from the adjacent cell zones. Now we are ready to launch our simulation. To launch the simulation, go in System folder. Here, go inside the control dict. Open it with Notepad. We are going to use the IcoFoam solver, which is a transient solver for laminar flows. We want the end time to be 5 seconds. We want time step of 0.03 seconds. We want the software to write our solution after every 20 iterations. We want the file to be runtime modifiable. This means that if we change any settings in this control dict while the simulation is running, those changes will get incorporated in the running simulation. Save this file. To launch the simulation, copy this icofoam command and paste it in your terminal by simply right-clicking here. Press enter. You can see that OpenFOAM has given us an error that patch type is not constraint type empty. That means the type of boundary condition for our default faces is not set to empty. To change the boundary condition, go in constant folder, go in polymesh and open the boundary file. Here you can see that the moving wall and the fixed walls have been assigned the type patch and default faces has also been assigned the type patch. We want to assign the type as empty for our default faces, and for the walls we will assign the type as wall. Save this file. Again go to the terminal and press the up arrow key to bring forth the command that we had entered previously. Press enter. Now you can see that the solution has started. You can see that current number is getting printed for each iteration. We want the max current number to be well below the value of 1. If current number exceeds the value of 1 or more, then there are chances that the current number may explode and the solution may get diverged. Let's wait for a few minutes until the iterations get completed. You can see that the software has simulated for time up to 1 second right now. If you go in your main folder, you will be able to see that there are some time step folders which have been created in the folder. These time step folders contain the results at each particular time step. That means the results of 0.3 seconds have been stored in this folder and so on. We can view the results by going in Paraview. Close the case.foam by clicking on delete and open it again. Press on apply. Finally, we can see some colors after the black screen. Currently, we are viewing the pressure on our lid-driven cavity. We can change it to view the velocity. You can see that the velocity is now being displayed on the screen. How to read these legends? Red color indicates that the value of velocity is 1 meters per second. Blue color indicates that it is 0. You can see that we had assigned a velocity of 1 meters per second to the top wall, and it has correctly assigned that same velocity in the simulation results. But this doesn't show us that the fluid is moving inside the domain, because this is just the first time step. We can increase the time steps by clicking on next frame, and you can see how the evolution of fluid flow inside the lid-driven cavity is taking place. To go to the last time step, click on last frame button. Click on rescale to data range. You can see that the velocity of fluid is now changing as we are changing the iterations. But this is still not showing us the direction of the flow. To view the direction of the flow, select case.foam and click on glyph. Click on apply. This will plot the vectors on our fluid domain. We will change the size of the vectors to 0.05 by making changes in the scale factor option. Click on apply. Hide case.foam. Here we are currently viewing the pressure. To view the velocity, select the glyph vector. Rescale to data range. You can now see that the fluid is moving with 1 meters per second in the right direction, that is the positive x direction, as we had mentioned in our U file. The fluid is moving because the wall at the top is moving. One of the interesting properties of fluid is that it tries to stick to any wall surface that it can find. The fluid which is adjacent to the wall surface tries to stick to the wall surface, and when the wall moves, the fluid adjacent to the wall moves along with it. But it cannot go outside our boundaries of fixed walls. That's why it tries to come back into the domain, and thus this sets up a recirculation zone inside our fluid domain. This is the result for time at 1.2 seconds. You can see that the software is still calculating. We can load the new results here by simply clicking on case.foam and click on refresh, because I want to load the results of the new time steps that have been created. Once you have clicked on refresh, click on the last frame button. You can now see that the solution has changed a bit. If you go to the first time step, you can see that initially the fluid was not really moving much inside the fluid domain. But in the last time step, you can see that a recirculation zone has been set up due to the moving wall in our fluid domain. This is how we can set up flow inside lid-driven cavity problem from scratch using Salome, OpenFOAM and Paraview. If you have found this video helpful, don't forget to share it with all your friends, and don't forget to press the like and subscribe button on my YouTube channel. We will meet again in a new video with a new OpenFOAM tutorial. Goodbye till then.